Last time we worked on reviewing exponential functions. Today we're going to review our logarithmic functions. So we're going to start by talking about what is a logarithm. So here is a graph of 10 to the x, which we graphed last time, and we said all exponentials go through the point 0, 1, and then our next point 1 is whatever the base value is, which in this case would be 10, so 110. This is an exponential that's growing really, really fast here. And so it looks like this. Well, logarithm is the inverse of an exponential. And so in order to draw that logarithm, we would take these x and y values and we would switch them. So here we go. The point that was at 0, 1 happens at 1, 0, and the point that was at 110 is going to go to 10, 1. And so this gets really close to the y-axis and then grows this way. That is a logarithm. It is the inverse of an exponential. So this would be a log with a base of 10, and this would be the exponential 10 to the x power. If we had 2 to the x, its inverse would be log base 2 of x. If we had 3 to the x, it would be log base 3 of x. So every single log is going to go through the point 1, 0, since every exponential goes to the point 0, 1, and they are inverses. The next point over is always going to be the base and then 1. So this was a log with a base of 10, so we've got the point at 10, 1. If it was a log base 2, it'd be 2, 1. If it was a log base 3, it'd be 3, 1, and so on. All right, so let's write down some of the things here to the right that we know about logs and exponentials. So the domain for exponentials, we said, was all real numbers, negative infinity to infinity. And it started at 0 and went up forever with a parentheses. Well, the domain for a log starts at 0 and goes to infinity. It is getting really close to the y-axis, but not touching it. So we've got a parentheses there. It's everything to the right of that y-axis. For our range, it is all real numbers. These are inverses, so notice that they switched. The domain here became the range, and the range became the domain. This one had a horizontal asymptote at y equals 0. Our exponential here had a horizontal asymptote at y equals 0. Our logarithmic has a vertical asymptote at x equals 0. And remember, we do have to write the x and y equals because that's a vertical line or a horizontal line. All right, so let's talk about this definition of a logarithm. A logarithmic function is the inverse of an exponential function. We just said that. And so here we said that, I'm just going to put an example of one, b to the x equals n. To rewrite that as a log, we said the base on the exponential is the base on the log. So we would get a log with a base of b of n is equal to x. So the base of the exponential became the base of the log, and then these two basically switch places. Right here, this n is said to be in the place of the argument. The argument is the part that you're taking the log of, and then our answer would be here. So our exponent becomes the answer, and our answer becomes the argument here. It's important that you're able to switch from an exponential to a logarithmic, because when we start to solve, you're going to have to be able to switch them. So we've got 8 squared is equal to 64. If I was to write that as a logarithmic equation, and I'm going to go ahead and write this in the center just so that you can see what's happening. I like to remember to switch these over by dropping the base, so log base 8, and then these two switch. So 64 becomes my argument, and 2 becomes my answer. So 8 is the base, it drops, and these two switch. So my answer here would be log base 8 of 64 is equal to 2. And so for my next one here, we would get a log with a base of e of 2x is equal to x. For this next one, the base on the exponential is the base on the log. So that would be a log with a base of 164. And this is the base, so it should be smaller and showing on the bottom there Then 1/8 becomes the argument, so that's the regular size. And then 1/2 becomes my answer. That too is the regular size there. Notice that the 8 is smaller into the bottom here, so is the E. And then our last one is log base 16 of 4 is equal to 1/2. Now, just like we went from exponential to a log, you should be able to go from a log to an exponential. So here is the bottom ones. And again, I'm going to show you that diagram off to the side. So if I have log base 7 of 49 is equal to 2, just like we drop the base on the exponential, we drop the base on the log. So it becomes 7. That does go from being the little number to the big number here. And then the switch, so that is 7 squared is equal to 49. 7 squared equals 49 on that first one. Feel free to pause the video and try them and then check your work. But our base here is 10, so we drop the base and then those switch, so that becomes 10 to the 4th equals 10,000. And 5 to the 0 is equal to 1. That's an easy one to check because you know anything to the 0 power is 1. And 2 to the negative 3rd equals 1/8. Another easy one to check, you know that when you have a negative exponent, that means to flip it. So we get 1 over 2 cubed, and 2 cubed is 8. All right, that I told you you're going to have to be able to do that because that helps you identify what some of the answers are for solutions on problems. And so we've got n equals log base 10 of 100. So in order to evaluate this, we can drop this base and switch. So we get 10 to the n equals 100. And then we know that 10 to the 2nd power is 100. So I was able to evaluate this without a calculator by switching it to that exponential. Same thing here on the next one, we get 8 to the n is equal to 8. And so that means n has to be to the 1st power. This one here would switch to be 9 squared is equal to n. Well, we know 9 squared is 81. So again, we're able to evaluate that missing term. Here we've got 4 to the 0 equals n. Anything to the 0 power is 1. So we know that n has to be 1. And feel free to pause again and try some of these on your own so that you can check them. Here we've got n cubed is equal to 125. And so we would take the cube root of both sides. That cancels out, freeing my n, and the cube root of 125 is 5. Notice I'm doing these without a calculator. You don't need a calculator to do these. A lot of these you're going to be able to set up and then figure out by doing the simple math. So we've got n cubed equals 1/8. Again, we would take the cube root of both sides. And so my n is freed, and the cube root of 1/8 is 1/2. Because that's what would multiply times itself 3 times to give you the 1/8. Here we get 1/4 to the 3rd power is equal to n. And so 1/4 to the 3rd power, that's 1 over 64. Because 1/4 times 1/4 is 1/16 times another 1/4 is 1/64. N to the negative 2 equals 149. We know that in order to get rid of a negative, we flip it. And so that would be 1 over n squared is equal to 1 over 49. And so n has to be 7 to give me 49. And then for our last one here, n to the 1/2 power is 16. Sorry, wrote that one backwards. Let's fix that. 1/2 to the n power is equal to 16. In order to do this one, I know I want to flip it. So the 2 goes up there to give me a positive number. So I know n has to be negative to flip it up and be 2 to a power. And so 2 to the 4th power gives me 16. So n would be negative 4. That's a tricky one, but we've got that one. All right, since a to the 0 is equal to 1, then log a of 1 is equal to 0. So anytime that we have an argument of 1, it's going to be equal to 0. If you remember that, that's going to help you evaluate a lot of things. So anytime that we have an argument of 1, it's going to be 0. And this one would mean log A of A is equal to 1. So anytime that the base and the argument are exactly the same thing, then it is 1. They cancel each other out, basically. So that's this property listed right here. Log base B of X is X because this cancels. And B to the log base B of X also cancels, just giving you the X. So that's an easy property to remember. All right, there are 2 log bases that are used regularly that we call by a different name. So log base 10 of X is called the common log, and when we write it, it is just Y equals log X. You don't have to write the base if it is a 10. That is called the common log. I want to go ahead and show you that on the calculator because when you're using the calculator, there is a certain button for that. So right here, here's our calculator. To the left of 7, you'll see the common log button. Anytime you push this button right here, it is talking about the log with a base of 10. If you forget that, it does have the 10 to the X right on top to remind you that is the common log. So we've got the exponential and its inverse, the log with a base of 10. If you want to put any other log base, then you need to change the base. And so we do that by doing alpha window, and then it goes down here to log base number 5. That allows you to put any other base in there. But anytime you use this log button to the left of 7, that's a base of 10. The other one we use often, this should not say ln, it should say log. Log with a base of e to the x is, we write as lnx, and that is called a natural log. So the natural log is ln of x, and that's when you have a log with a base of e. That one's right below the log button in the calculator. So this ln right here, that stands for the natural log, and that's a log with a base of e. Again, if you forget that, its inverse is right on top here with e to the x. So the inverse, e to the x, and natural log are right there. All right, so the ones that we were just talking about with the log base b of b, remember that cancels and that's 1. This is the common log, so it's got a base of 10, so these are the same and that would cancel and be 1. The natural log is a log with a base of e, and again, that cancels and is 1. E to the natural log of x, that cancels, so that is just x. And the natural log of e to the x, those cancel, so it's just x. So those are some easy ones to remember that help you with solving. All right, so now that we understand that exponentials and logs are inverses, let's go ahead and work with this log base. I've gone ahead and written out the transformational form up here so that you've got it with you. This has all of its transformations A, B, C, and D. And remember, it doesn't matter which parent function you're dealing with, they all work the same with transformations. So we're going to talk about the vertical transformations and the horizontal transformations here. For the translations, for vertical, we're talking about D. So if it says plus D or minus D there at the end, this is up and down. For the horizontal, that's talking about C. And when it says X plus C, it goes to the left. And when it says X minus C, it goes to the right C. Because remember, minus is that part of the formula. So if C was negative, the minus and the negative would cancel out and turn that into plus. That's why that goes to the left. All right, for our reflections, if the A value is negative, it reflects across X. And so that's out here. So if we've got a negative out here, that reflects it across the X. If the B value is negative, then it reflects it across the Y. And so that's here. If the negative is right in this part of the equation, then it's going to reflect it across the Y. For our vertical stretching and compressing, if A is greater than 1, it is a vertical stretch by A. If A is between 0 and 1, it is a vertical compression by A. That is the scale factor right there. And it is a vertical stretch if it's bigger than 1 and a vertical compression if it's between 0 and 1. We're just talking about the numbers. So if it is -3 right here, the negative would be a reflection across the x, and the 3 would be bigger than 1, so it would be a vertical stretch by a. That would be two separate ones. Here you're only looking at it as an absolute value, just that number. If our b value is greater than 1, it is a horizontal compression by 1 over b. And if the b value is between 0 and 1, it is a horizontal stretch by 1 over b. What that means is that you need to flip it to get this scale factor. So if there was a 3 right here, we would say that was a horizontal compression by 1/3. You've got to flip it. If this was 1/4, we would say that's a horizontal stretch by 4 because you flip it for that scale factor. All right, so we're going to look at some of these right here to determine what our transformations are. This right here has two transformations. The base is not a transformation. That's part of the equation. This is not in parentheses, so the x is the only argument. +5 would be our d, so this would be up 5. And this would be a vertical stretch by 3 since it's bigger than 1. In this case, we have a negative here, and then we've got the 2 there. This is inside of the parentheses, so this is part of the argument. So that's our c value. So this is going to go to the right 2, and then this one's going to be a reflection across the x. And then for our last one here, we've got 1, 2, and 3 transformations. The 1/2 that we're multiplying by, that's our a value. Since that is between 0 and 1, that would be a vertical compression by 1/2. This is to the left 2, and then down 4. All right, so we take those transformations and we use our parent function to graph this. So we're going to look at graphing some. Here is one full equation. We've got two transformations here, a left 5 and a down 3. We start with the parent function. And so the parent function to this one would be a log base 2 of x, because this has a base of 2. And so this would be our starting point. You want to make sure you know those parent functions. But we said that's the inverse of 2 to the x. So here is our inverse. That's our starting point right there. We said every log goes through the point 1, 0. And then the next point over is whatever this base is, 1. So our next point there would be 2, 1. 2, 1, and 1, 0. Those are the key points right there. You can start and graph your parent function first, always, and then apply the transformations to draw the new one. So I'll draw the new one in a different color. So here we go. For our transformations, we're moving to the left 5 and down 3. If you think about your vertical asymptote here, if I move up or down, that doesn't change a vertical line since it goes infinitely up and down. However, the left 5 does change that vertical asymptote. So that's the first thing I would want to draw is my new vertical asymptote, which would be at left 5. So it's over here at x equals -5. Now I take each one of these points and I apply those transformations. So left 5, 1, 2, 3, 4, 5, and down 1, 2, 3. We do the same thing for the next point over. It's at 2, 1. And so I move that to the left 5 and down 3. And then we get really close to the asymptote and we move across to the side. And that would be my new graph. The domain for that one is going to start at -5. And again, that would be a parentheses and it goes to the right forever. Our range is all real numbers. And sometimes when you put that in the graph, it doesn't look like that when you put it in the calculator. So I want to make sure that we look at that and talk about it. Again, to put this in, I would do alpha and then window. And that allows me to change to whatever log base I need. So I'm going to pick the log base there. And I'm going to put in my 2 for the log base, x plus 5 in the argument, and then the minus 3 at the end. And then I hit graph, and there is my graph on the calculator. It looks like it cuts off right here. That is just because of the pixels of the calculator. That continues down forever. Your calculator just doesn't have that kind of high definition to draw it all the way down. The range for all logs, though, is all real numbers. This is always increasing. It starts down here and it is increasing forever. So that's going to match my domain, -5 to infinity, and that is going to be increasing the entire time. And then my asymptote is at x equals -5. Remember, it does have to be x equals because it's a vertical line. All right, for our next one here, -3 log x plus 2, that is up 2, and that is a vertical stretch by 3, and then our negative is our reflection across x. In this case, since it has not moved left to right, our vertical asymptote is still going to be at 0. Now we start to apply those transformations. So the point that's at 1, 0, 1, 0 is right here. If I multiply that times 3, it's going to do nothing because 0 times 3 is still 0. If I reflect it across the x-axis, it's not going to do anything because it is on the x-axis. So the only transformation that's going to touch that one is the up 2. Now this is the common log. Since there's no base written here, 10, 1 would be my next point because that's the common log. Oops, just move my pencil there. So 10, 1 is my next point. When I multiply that times 3, it's going to go up here to 10, 3 because 1 times 3 is 3. I reflect it over the x-axis. So now I am at 10, -3. I then move it up 2. And that is my next point right there at 10, -1. When we apply our transformations, the vertical stretches and compressions come first, reflections, and then the translations. And then I just move really close to my asymptote and connect my points. In this particular graph, it is decreasing the entire time. It starts from up here and it is going down. So this would be decreasing, and it's going to follow my domain of 0 to infinity because it is decreasing through the entire graph. And again, the range of all logs is -infinity to infinity. We'll go ahead and look at one more. This one right here is as tricky as it would get. It is not in the transformational form the way it is right here. So we would want to get it into the transformational form first. We do that by factoring out that negative. There could be nothing in front of the x. So if there's something in front of the x, you're going to want to factor that out. So we factor out the negative. Negative times x, negative times -5 would give me that +5. If you don't do that first, you're going to end up saying it went to the left 5, and it did not. It went to the right 5. And that is a reflection across the y, since it's in the place of the b. And that is a vertical compression by 1/2. All right, this did move to the right 5, so I'm going to have a vertical asymptote at x equals 5. And now we're ready to start with our points. So the point at 1, 0. If I vertically compress it by 1/2, 0 times 1/2 is still 0, so it's still at 1, 0. Now I can reflect this across the y-axis. It goes over here to -1, 0. And then I move it to the right 5, 1, 2, 3, 4, 5, and my new point is right here. I then go to my point at 10, 1. When I vertically compress it by 1/2, it is at 10, 1/2. I reflect it over the y-axis, so that comes over here to -10, 1/2. And then I move it to the right 5. I move towards my asymptote, so my graph looks like this. It is very slowly increasing, but it is increasing. It comes from down here and it's going up. So this would be increasing the entire time. of my domain, which my domain is from -infinity to 5. This is moved to the left side of the asymptote, so it's coming from -infinity to 5. Our range, again, is always all real numbers for all logs. And so that's our log graphs and an introduction to what those logs are.